Okay, Rob and George Andrews, welcome to the Tailwind Podcast.
Yeah, thanks for having me. Excited to be here.
So we're here to talk about your book, How to Kill an Asteroid, which has become particularly timely since we planned this conversation probably 2 months ago. So first of all, can you talk about your background and why you decided to write this book?
Yeah, so I'm a volcanologist by training. I love volcanoes. I've always loved volcanoes. I've always loved space things, the sort of things that all kids generally like. And, when I went into academia very briefly, I think I prefer telling stories instead rather than actually like doing the science of it. So, yeah, I like things that are like huge, colossal, sometimes awe-inspiring, sometimes frightening forces of nature that we for a long time could do nothing about. And so volcanoes is an obvious one. And asteroids has always been another. And the reason I wanted to write this book was not to scare anyone. It's because asteroid strikes are the only natural disaster that you can prevent. Not just slow down or mitigate, but you can completely stop with quite simple technology. So it's sort of something where everyone wins. And that seemed like a really good feel-good story to me to tell.
Totally. And just to get definitions out of the way, so the book focuses on the topic of planetary defense. How would you define that term?
Yeah, so it sounds alien-like, doesn't it? It sounds like an Independence Day type thing, which, it's not, the technology isn't like a million miles away from what you'd use, I suppose. But yeah, planetary defense, it's a relatively new term, despite the sci-fi sound trappings of it. And it means essentially you want to stop asteroids and comets crashing into the planet. That's essentially what it means, which I think we can all agree is something we all want to stop. Like, no one wants that.
So up until the mid-90s, planetary defense as a scientific and a policy topic had a bit of a giggle factor, as described by a guy named Clark Chapman, who's a planetary scientist. What was behind that giggle factor, and why did that start to change in the mid-90s?
Well, part of it was that it did really sound sci-fi. Like, people assumed that asteroid impacts, at least in the 90s, was something that happened to the dinosaurs. I mean, paleontologists, geoscientists were just coalescing quite confidently around the idea around 1990. Like, everyone was like in pretty much full agreement that the reign of the dinosaurs ended when a 10-kilometer meteor crashed into the Gulf of Mexico kind of area. Or the Gulf of something. And that was a colossal globe-changing thing. And it was happened so long ago that even those in the community, you couldn't really get the idea that actually we get hit a lot more frequently. And it really took like a warning from the heavens itself, really, to get people really buying into the idea that Earth could get hit again with something, So until then, it was like dinosaurs, sci-fi, Star Trek stuff, all like cool stuff, but nothing that anyone thought was like a real tangible threat.
Right. And in the mid-90s, or I guess more in the late 90s, there were two kind of big Hollywood movies that came out that sort of centered around the topic of planetary defense. Was there an event that prompted that?
Yeah, so these movies, like Deep Impact and Armageddon, like one's a comet, one's an asteroid, but the fundamental principle is we haven't got much time and they're going to kill everyone, basically. There was, in 1994, a comet had broken up and was orbiting Jupiter, as astronomers later discovered. And it's quite unusual because normally when you look up and you see a comet, it's one solid bit of ice with a nice, beautiful tail coming off it. But these astronomers saw that it was in like 24 pieces. And fortunately, they worked out along with NASA that it was going to crash into Jupiter, dozens of times. And everyone got very excited about that. And when they watched it over the course of a week, these giant shards of a comet, any one of which could wipe out like a billion people on Earth, crash into Jupiter, which barely noticed it because Jupiter's so big. And I think it was like 300 million atomic bombs worth of energy total unleashed on that thing. And even though it was very cool and very impressive, it really did make the scientific community sit up and think like, well, we don't want that to happen to Earth. And, 4 years later, perhaps not coincidentally, two movies about, stopping great big space things crashing into the planet came out because, what if that did happen?
Right. Great movies, by the way.
Yeah. One's very melodramatic, right? And one is like just action drama, and they're fun to watch.
Yeah, totally. So your book focuses on a particular planetary defense test mission called DART, which stands for Double Asteroid Redirection Test. At a high level, can you describe the DART mission?
Yeah, so the DART mission, like, it's no coincidence that it's called DART. All these scientific things are acronyms. They basically come up with the thing and then work backwards. But it did have two asteroids. So for a long time, like 2 decades at least, people in the European Space Agency and NASA were trying to think, like, how would we test a planetary defense technique? And it was quite hard to imagine how you'd do that because as you imagine, if you fly a spacecraft into an asteroid to ram it and try and deflect it, how would you see that that's happened? You'd probably need two spacecraft, right? You need one to get there and set up the camera, and then one to crash into it. Now, that was the original plan for a while, but everyone was like, that's too expensive. We can't really do this sort of thing. And then a very clever person, Andy, at Johns Hopkins University Applied Physics Laboratory in Maryland, thought, well, we don't need two spacecraft. We just need two asteroids. We need something where it's like the Earth in the middle, like a bigger asteroid, and like an asteroid moon going around it, a smaller one. And he reasoned that if you rammed into the smaller one with a spacecraft to try and deflect its orbit around the bigger one, that would be good for two reasons. One, that asteroid is not going to fly off into space and do anything dangerous. And two, like watching sort of like the pulse of a lighthouse from very far away, you could see the kind of reflected light of this two asteroid system change. So you could see that the moonlet would slow down or speed up depending on what you wanted to do. And the pulse of that reflected light would change. So you didn't even need two spacecraft. So they came up with an idea to deflect an asteroid, a harmless asteroid, in a way that was sort of cost effective enough that you could see it from Earth and you wouldn't need two spacecraft. So the Double Asteroid Redirection Test. And the target asteroid was called Dimorphos, which just means twin, basically.
Some people would say, hey, we've got nuclear weapons now. There's an asteroid coming towards Earth. Why don't we just fire those at the incoming asteroid and essentially blow it up? What are the arguments against doing so?
Yeah, so everyone in the community, even those who research like the nuclear option, like that's basically their job is to research this, always say it's not a tool of first resort. Now, some people don't say it's a tool of last resort. Some people do, but some people don't. But no one says it's a tool of first resort. And there are a couple of reasons. One is the geopolitical situation right now, for example, is not conducive to, hey, let's launch nukes into space on giant rockets. You know, it would require quite a careful consideration of how that's communicated, how people agree on that. You know, it would seem that the vibes are not right for that kind of thing. There's also a risk that, you know, a nuclear armed spacecraft could explode in atmosphere, which is not great, or on the launch pad. So you don't want to accidentally create a dirty bomb when you're trying to save the world, or even just test a turn to save the world. And the other thing is, like, there are other ways to deal with an asteroid, to deflect it. And the nuclear option is basically if you are short on time and you need to like really give that asteroid a push, like swat it in the other direction, or you opt to destroy the asteroid in a way. It's not as easy as people think, but basically, like if for like a Hail Mary approach, if you haven't got time to deflect it and it's small enough, you could vaporize it. There are studies that show you could do that sort of thing. But yeah, the main issue against it is really the geopolitical one. Like the technology wouldn't be too difficult. It's really just, if you can imagine a situation where there's an asteroid coming towards us, for example, and one country says, well, we're going to try and deflect it with something like DART, and another country says, we don't think that's going to work, we're going to launch a nuke at it. That's a tension you don't really want to have. You know, you want everyone to be in agreement on how it would work. And nukes are weapons of mass destruction. So pitching it as a tool for salvation is a bit of a hard ask, even though it is an option. So yeah, it's a sticky situation.
Yeah, it seems like it. Well, to start at the beginning of the planetary defense process, which is observation, do you think that we have an effective network of observation telescopes? In other words, how good are we at spotting potentially dangerous asteroids?
So much better than we used to be, but there's still a lot of work needed to be done. And it's taken longer than anyone, I think, would agree feels is necessary. So America is the clear leader in this. The European Space Agency has like agreements with observatories that can look out for these things, but generally it's observatories that can do some asteroid observation stuff, and they're very willing participants, but it's not like it's very decentralized. Whereas in America, NASA is the agency you go to, and they have the Near Earth Objects Observations Program, and they have been funding that for quite a while. The funding for that jumped dramatically during the Obama administration, I think the first term, which was nice. And basically, there are networks of telescopes around the world that NASA directly funds just to look for near-Earth asteroids and comets, which is fantastic because they are really good at that. They've discovered tens of thousands of these. Almost all of them have not been a danger or not perceived to be a danger. And the problem is they all rely on like reflected light. Now, when you're looking at reflected light for an asteroid, a giant asteroid, you know, like the planet killers, like the ones in the movies, they exist, but they're very, very few and far between. And they're like giant mirrors in space. Super easy to see. That's great. And none of them are a threat. And they think they found pretty much all of them. So that's lovely. But when you get smaller and smaller asteroids, which are still of a dangerous size, they're increasingly hard to see. And also, unless you know what the asteroid is made of, you can't tell if it's like a chalk-like asteroid that's reflecting a lot of light or a dark charcoal-like one that's kind of dull. So you can't tell the size of the asteroid, and it's harder to track. So that sort of stuff is great. But as it stands, just relying on this optical light astronomy on Earth is good, but like it's taking a while to find what people call the city killer asteroids. You know, there's still a good 10,000 plus of them in near Earth orbits that are still proving slightly difficult to find. You know, they'll get there eventually this way, but who wants to let people take their time in this? You know, you really want to find these things as quickly as possible, and everyone agrees that more needs to be done in that respect.
Right. And to that end, what is the near Earth orbit surveyor? Like, what sort of gap in our observation is that trying to fill?
Yeah, so Neo Surveyor is so cool because it's fundamentally very simple. And the person in charge of that, Amy Mainzer, came up with this idea, I think it was like 15 years ago or something like that. And it was, instead of use visible light, it's use infrared. Now, in infrared, asteroids, no matter what size they are, show up. If they're bigger, they glow bigger. If they're smaller, they glow smaller. And if you have a really sensitive infrared scope, you can even see them in the glare of the sun. That's one of the main problems of like looking for asteroids. If you look at the sun, don't do that, by the way, it's very blinding. So you can imagine trying to find an asteroid hiding in the glare of the sun in that part of space is basically like holding up a lit match in front of a thermonuclear explosion. You're not going to notice the match kind of thing. So infrared, you will see these sort of things. So it will find 90% of these like 460 foot or 140 meter across asteroids that are the class of asteroid that would, if it hits the city, would vaporize it. Like, they're called city killers for a very good reason. It will find 90% of those within like a few years, a decade maybe. And it's launching, I think 2028 is when it's scheduled to launch. It will launch into space. And the reason it's launching into space is because it won't have to deal with the atmosphere. The atmosphere gets in the way. It won't have to deal with satellites that get in the way of increasingly getting in the way of a lot of telescopes. Mm-hmm. And it will have special paint on it, coated like very black. It will have a sunshade on it. So it'll be one of the coldest objects in the universe. And that means its infrared scope will be like ultra sensitive. So its sole job is to look for these like killer asteroids. It'll be incredibly good at it. Like, there's no debate. Like, the science is just unambiguously certain. It's just a simple principle, all for the low price of $1.2 billion, which might sound a lot, but imagine if it discovered an asteroid coming towards us that we wouldn't have been able to see otherwise, and then we'll be able to defend ourselves against it. Like, the cost-benefit ratio for that is fantastic, you know, so it's a very cool mission.
Totally. And if you look at like NASA's annual budget, it is a great bang for your buck.
Yeah.
I would also imagine that $1.2 billion is spread out across different years. So it's not like a $1.2 billion hit in one budget cycle.
It's like for staff, operations, launch, putting it together, you know, it should have been done earlier. Like, I think people keep saying it could have been done 10 years ago, but it was put in the way NASA decides how they do missions. For most of them, they put them through like a competitive gauntlet where people put up their ideas, they get teams together, they say how they're going to do something. And for a long time, planetary defense and planetary science, think of like the Voyager missions or something like that, were put in the same category, and they had to compete with each other. Only in 2019 did like the very senior staff at NASA go, this is silly. You can't do planetary science if we're all dead. So we need to put this in a separate category and give it its own funding stream. And even though there's some problems there, it was finally confirmed in 2022. But everyone I speak to says like that could have been done 10 years earlier. So I'm just glad it's happening.
You mentioned the scientists and the researchers behind it. And in order to write this book, you spent a lot of time with the planetary defense community. What is that community like? Because it seems like to me that they are very passionate about the work that they do. And there's also an understanding that the work that they do is not the most well-funded area of research in the world of space. So what is that community like?
They are like, for people who are kind of dealing with a risk that could have essentially be existential, are just so chipper and cheery and so steeped in like geek lore, you know, like everyone. I love the fact that the person at the time, Lyndon Johnson, who was in charge of the NASA's planetary defense effort, you know, basically got into it. I mean, he was in the Air Force, but he loved astronomy, and he, you know, there's a Star Trek episode from 1963 where they deflect an asteroid away from a planet, and he was like, awesome, I want to do that kind of thing. Mm-hmm. And the second in command, who's Kelly Fast, who's now in charge, the acting head, she basically grew up in Hollywood, and she could see the Griffith Observatory from a window and the Hollywood sign. So she was taken to the premiere of Star Wars in 1977, was like, cool, amazing. So these are people who are just like, they're really driven by, yes, there is this noble goal, but there's no sense of an ego. Everyone just loves the fact they get to work on something that is essentially it's saving lives. They're not even around yet, on timescales that, like, if this technology works, if these things work, then whenever it's needed to be deployed, it could knock asteroids away, see these asteroids coming without anyone even, it wouldn't even make the news eventually. It would be so routine, So they are so humbling in the fact that they don't have any ego whatsoever. They're just the loveliest people, probably the best, nicest scientists I've ever had a chance to chat with. Just very, very down to earth, very down to earth.
That's awesome. How does the chemical composition of asteroids and comets factor into planetary defense? Because you explained in the book, I thought that these were just like very sort of hard space rocks, but that's not always the case, right?
Yeah, honestly, the weirdest thing I've ever found out about them, and scientists have been finding out about this for quite recently. It's not like it's been known for ages, because, they've only recently been landing on asteroids and seeing what they're made of. Asteroids that are like planet killery size, and we're talking like a kilometer or bigger, 2/3 of a mile bigger, they're probably a bit more solid, but maybe covered in rubble and things like that. But asteroids of these city killer sizes, or even smaller, tens to hundreds of meters, seem to be like you're walking on a ball pit or something. Like they've got the consistency of cappuccino foam, someone said to me. I remember someone said, like, how do you fight with foam on a beach? How do you deflect something that is like boulders and cliffs flying in close formation? Space is weird, gravity is weird, and essentially it means that there's a kind of a pro and a con here. Like, if you want to deflect an asteroid, if it's a solid rock, it means you could just hit it as hard as you want, basically, essentially, and it would be a lot more like playing pool or something. Like, you would deflect it out the way, it would respond cleanly. If you hit something that's like a pile of boulders all flying in formation, you could fragment that into bits going everywhere. Now, you don't want an uncontrolled situation where you've turned a cannonball coming at Earth into a shotgun spray. That's just a different kind of bad. So the sort of physical makeup of these asteroids matters a lot. And, it means that when you want to deflect an asteroid, you want to hit it hard, but not too hard. Because if it's big enough, you don't want to break it into like smaller but still dangerously sized chunks. So it's like a huge, I wouldn't say necessarily a problem, because the benefit is if you hit these asteroids just right, a lot of debris comes off of them because they're so weak. And that debris acts like a rocket pushing the asteroid even further in that direction. So there's like good and bad sides to this. Like, if you hit it just right, you hit it really hard. But if you go slightly too hard, you'll break it into a dozen pieces. So they're weird. Like, asteroids are just weird. So it matters a lot. Yeah, it matters a lot.
It's a complicating factor in all of it. So to what degree is Earth directly in the firing line, so to speak? I mean, have we historically had a lot of asteroids head our way, but they essentially burn up in the atmosphere before we get hit?
Yeah. So our atmosphere is like the thing that is our safety net. It eats up a lot of asteroids that are like a meter to 10 meters. 10 meters is kind of rare, but we get hit by like 1 meter sized asteroids all the time. And they're basically like shooting stars, but just way brighter, brighter than the full moon when they happen. And they always look amazing. And every couple of months that kind of happens, maybe even more regularly. Earth does get hit a bunch though. And it wasn't that long ago. It was only 1908 when for sure an asteroid that was about 40 to 60 meters across hit a remotest part of Siberia, and it was like a 12 megaton nuclear explosion. So that doesn't happen often, fortunately. The bigger the asteroid is, the less often it hits us. Right. But we do get hit by these things, and no one's got any idea. It's not like there's no schedule. It's like a volcano. It doesn't erupt like on a schedule. I think a lot of people think if you hear a phrase like, oh, this only happens once every 1,000 years, it doesn't mean we wait 1,000 years between these events. It means that's just an average. It's surprisingly a common like misconception, these things. And the same with asteroids. I mean, that kind of 1908 thing, I think it was like some people think, oh, it's a 1 in 1,000 year event, but some people think it's a 1 in 50 year event. So you can see how like it's really, no one's really sure. But we get hit a lot, but we have an atmosphere. So mostly it's okay.
So speaking of, there's been a lot of headlines recently. There's an asteroid named YR4. And I'm sure you've been getting a lot of texts about this. People have been reaching out to you. So what's your take on it so far?
Yeah, I'm unsurprised. I've written a lot about this asteroid because a lot of people for the first time, understandably, are finding out like, okay, what is this planetary defense? Like, what do we do? And asteroid is 2024 YR4. It's not a particularly catchy name, but if this orbit is studied for longer, it will get a proper name. And I think because it's an asteroid of interest, it will be given a proper name. So this asteroid is somewhere between 40 and 100 meters across, 40 and 90 meters across maybe. And it was discovered on the 27th of December last year, 2 days after Christmas Day when it made its close flyby of Earth. Good thing it didn't hit us then, because an asteroid on the lower end of that size range, so 40 meters, if that hit a city, it would be a bit like the 2013 meteor that hit a Russian city called Chelyabinsk, but like on steroids. So 2013, an asteroid that was 18 meters across blew up with a force of 500,000 tons of TNT in the sky, and it smashed a lot of windows, and people got blown off their feet. People got sunburned. About 1,600 people got injured, mostly through like shotgun sprays of glass blowing inwards. This, if it's 40 meters, it would be like, tens of times more powerful than that. So it'd be like a small nuclear weapon going off. It would cause serious injuries to death nearby, many minor injuries everywhere else. It would not be nice. On the higher end of that size range, 90 meters, it would be like a large nuclear weapon going off in the city, and much of that city would be destroyed in the middle, and there'd be deaths and injuries, tens of thousands, hundreds of thousands, millions, depending where it hits, if it hits a city. So this is a serious asteroid, and the problem is there is currently, based on current observations, a 2.1% chance that on December the 22nd, 2032, it will hit somewhere around the equator. That's a disquieting number. I mean, it's not something you should lose sleep over, but, 2% chance is not nothing, and it's basically, if it gets over 1%, it activates like the planetary defense community. They want to either rule that out or know it's a problem. And they've got a couple more months of observations, and they're hoping they can rule it out by then. But if not, we have to wait until 2028 when it comes around again for a safe flyby. So it's an unusual situation. It's definitely a dangerous asteroid that could threaten certain parts of the world, or it could land in the ocean and harm no one. But yeah, it could be a problem.
One of the parts of your book that stuck with me the most is the simulation exercise. So basically in 2022, they do this sort of like war game scenario for an asteroid coming towards Earth. And there's scientists and researchers that are participating in this war game exercise, basically. And there were a lot of interesting takeaways from that. One is we don't know exactly where an asteroid is going to hit until pretty close before it actually hits. Like we might know the general kind of region or something like that, but it might even hit in different countries. You might not know the exact city, stuff like that. So I guess what were some of your main takeaways from that exercise? Because I think there's some parallels to what could potentially happen with YR4.
Yeah, so that's a bit that really surprised me. And it surprises people who even work in this community that there is a chance that you might not know exactly where an asteroid is going to hit until quite close to its impact date. You kind of have to get a bit lucky. So the asteroid has to kind of get really close to the Earth, and we get enough observations of it in enough time to kind of plot out that exact entry point. So in that exercise, the simulation was an asteroid that could handily wipe out a city was eventually found to be heading towards somewhere in North Carolina, a place called Winston-Salem, who volunteered themselves up to be hit. And what you really want to do when you're observing an asteroid is, instead of just this reflected starlight kind of thing, or even infrared, you want to ping it with radar. Now, this is where like the US is like super not invested in part of planetary defense, surprisingly. And if you hit an asteroid with radar, you need to be pretty close. You know exactly what size it is, pretty much, and exactly the trajectory. It's just like the most accurate way of knowing where an asteroid's going to go. And you don't necessarily get that. The asteroid has to fly close enough to Earth. And often that happens when it's about to hit the planet, basically. So you can know like a week or two before impact. Now, there were some capabilities that America used to have that no longer has that would have been helpful in this 2024 YR4 situation. I'm not 100% sure. There's some debate about it, but there was the Arecibo Observatory in Puerto Rico, and that collapsed quite catastrophically in December 2020. And even though there's a bunch of reasons why this collapsed, wear and tear and stuff, like it wasn't really getting the proper attention, people have said, over the time. Like a bit, it's sort of fallen into neglect, and it collapsed, and there's no plans to replace it. Now, that was easily the most powerful radar dish that under America's kind of like domain. And I think there was a chance that this asteroid that we're worried about now could have been pinged by this radar if we still had it, but it only has something called the Goldstone radar, which is can't transmit radar as far. So as a result, we don't know the asteroid's trajectory that accurately. Whereas if we pinged it, we might actually say, oh, this is where it would impact if it would be, narrow it down. So radar is like super helpful, but the asteroid has to get close enough to ping it. And like in 2028, when this asteroid comes back around again, I still think it's not going to be close enough. So there could be a situation where like the exact impact zone is not known. Now, imagine if you live on an impact corridor where like, oh, it could land in the ocean, or it could hit this city, or it could hit another country. How on earth do you tell who to evacuate when? Like, that's the real problem. Like, even convincing people where for sure an asteroid's going to hit. Like, in a week, your city will be hit by an asteroid. It's it's kind of hard for even me to imagine that. Like, I'm steeped in this stuff, and I would still, like, to convince people a ball of fire from the sky is going to come down and wipe out your city. That's hard enough as it is, but if you don't know where exactly it's going to hit, how do you evacuate a country? Like, that's never happened before, right? So some of the danger is not just dealing with the asteroids. That might be the easiest bit. It's actually like, who do you know how to help? That's the bit that's tricky.
Right. That was exactly one of my takeaways. I mean, there's obviously the danger from the actual impact, but then the interesting thing about asteroids is that you have years of trying to prepare for a potential impact in a given location, and there would be chaos that could ensue before. One of the researchers that participated in the exercise talked about the potential kind of impact of social media and how misinformation could really sort of cloud people's decision making and all this kind of stuff. And it wasn't until I read that section of your book that I realized how chaotic it could be before the asteroid actually makes impact, even in the years preceding it.
Yeah. I mean, that's the bit that really, like, in that chapter as well, like, even the people who are sort of dealing with the wargaming exercise, there's a quite, like, weirdly upbeat, right? They're like, oh, this is kind of fun. It's like, I think one of them compares it to playing, like, well, someone compares it to playing, like, watching, like, a horror movie or playing, like, a scary video game. Like, you want to get scared, but you know you're safe, basically. And also something good comes out of it. You're learning how to deal with an actual emergency. But when you talk about social media, I mean, oh man, they sounded so depressed because COVID had just happened, and everyone on Facebook suddenly became an expert on pandemics and, but also weirdly wary of experts. And it sounds like a crazy premise, but like, if there was an asteroid coming towards Earth, right, like, people would only have space agencies to trust, and they'd see these weird fuzzy images. And there's a part of like any population that would just be like, no, it's a conspiracy, or, oh, it's just to make us afraid of something else. Like, you wouldn't see it in the sky with your own eyes in the same way. And social media at the moment is not getting any better, is it? To be frank. So misinformation is still like such a paramount problem in every corner of society that I dread to think what would happen if, like, this asteroid, for example, 2024 Y4, is found to have a almost certain chance of coming towards Earth. That's not going to go well, I think, socially. So yeah, that's the only bit I'm pessimistic about, is like, what is the solution to misinformation? If someone can figure that out, that would be great.
Yeah. Well, in terms of defending against the actual impact, you talk about the budget for planetary defense. So in terms of the funding, do you know, kind of off the top of your head, roughly what slice of the pie of NASA's budget does planetary defense receive?
As NASA's total budget, I'm not sure exactly what NASA's total budget is at the moment, actually, because in the last few years, it's gone a bit crazy, like with everything, and now change of government, it's a bit unclear. I just know that it's about $150 million a year, which is incredibly small.
Yeah.
I think in terms of, like, as of a couple of years ago, if you compare it to because planetary defense is an international security concern. It's like, and I think it's like 0.015% of the annual US military budget sort of thing. So,
right.
Considering you're defending the entire planet, it's in everyone's, no one loses when you do this. It's so cheap. Like, it's kind of amazing. And to their credit, like, no one is saying, oh, we need so much more money to invest in blah, blah, blah. I think what people want is, like, the guarantee of, like, continued investment for what they need kind of thing. So that NEO surveyor mission should have happened ages ago. Even when it was like, okay, we're going to give it its own dedicated funding stream, the senior leadership at NASA was still not quite sure if they needed to give it all the money, even though Congress was like, no, you can have all the money. It really is like a rounding error on a spreadsheet for what it is, like, genuinely. So it's not so much that planetary defense is, like, underfunded. It's more that, although more would be good, it's more that, like, it's worrying that it's always uncertain. Like, is it going to continue to be funded? Are people still going to want this to happen? Like, okay, we've done DART, but, like, we need to test other techniques. Do you just want to, you can't just say we're done kind of thing, Yeah, and it's particularly nerve-wracking right now when, like, the new administration, there's no clear space policy at all except Mars or something. So people have no idea what's going to happen with any of these budgets. So yeah, continued support for it would be good. But yeah, it costs like nothing. Essentially.
Why do you think that there's sort of mismatch on that? Like, you talk about, there have been surveys done where citizens, over 50% of them, say planetary defense should be a top priority for the government. Yet there's been some historic kind of budgetary or funding issues for planetary defense. Why do you think there's a mismatch there?
Yeah, it's funny. No matter who I speak to, even people who are, like, really, like, steeped in, like, budget stuff, because I come from a science background, so when I have basic questions of, like, okay, this mission costs this, like NASA's own mission costs this. Why aren't they asking for that exact amount of money? People are just like, they've never given a clear answer. And I don't mean that like the planetary defense like office part of NASA. I mean like the senior leadership side of it, who decide where funding goes. There's no clear answer. No one likes to really talk about it so much. In last few years, there has been like mismanagement and like missions have like really spiraled in cost. Like the Artemis program, I want that to succeed. I would love to see American astronauts on the moon. I love the idea of like a permanent presence on the moon for like scientific research and everything like that. I think it's great, but like the Artemis program's costs are like in tens of billions. It's like just designing the rocket to take them there is just so expensive and gone through so many like trials and errors. It's a weird situation. Like the Mars sample return, that this very complex series of missions bring samples of pristine, maybe life-containing rock back from Mars. Way more expensive than they thought it'd be. They're currently soliciting calls from like industry to help make it cheaper. Or, I think like costs have run away in a weird way, with parts of NASA. Not because they have no idea what they're doing. It's just, it turns out when you want to do these really ambitious things, it sometimes costs more than you think. And they've had like missions to Venus cancelled, but they're not cancelled. So I think like there needs to be some reckoning there for sure. But all of this stuff is so cheap compared to anything else. All of these things deserve to go. But yeah, planetary defense should be like an absolute top priority. So the idea, like, why NEO surveyors had to go through these loopholes. I mean, every time I've asked the person in charge of that mission who joined NASA basically in 2019, like they're just constantly confused why this happens. It's all good now, but no one's really sure why. No one's really sure why. I think the idea of planetary defense is still competing with planetary science to some degree. And I love planetary science, but my goodness, we need to make sure that, the Earth doesn't get hit by asteroids. Like it seems like a no-brainer to me, but I think it's still, there's still some inertia there that it doesn't really have a good answer. There's no really good answer. If you ask people who are responsible, I'm pretty sure they'd say, well, we just messed up a bit. Sorry about that. It's better late than never kind of thing. So yeah.
Sort of a last question to wrap up. Robin, I'm curious, like originally I put this question on there not thinking that there was a potential asteroid like 2024 YR4 potentially coming our way. If there was an asteroid coming our way, what do you think, what defenses would be stood up against it, given the sort of different array of options that are out there right now?
There's 4 options that you can do. One is to deflect it with something like DART. The problem is a lot of studies and a lot of experts have said that ideally you want about 10 years to deflect an asteroid that's kind of the higher size range of this, 90 meters and above sort of thing, like stuff that could really wreck a city. Because you want to be sure you're going to deflect it emphatically enough that it won't be knocked away from the planet. You can't leave it to the last second. Like that's not, asteroids have a lot more momentum than any of our spacecraft. You can't just match it like punch for punch. So you need quite a lot of time to hit it so it moves gradually out of the way. You don't want to hit it too hard so it breaks. You might need multiple impactors. It might not just be like one giant impactor. You may need several smaller ones to hit it several times. But yeah, it's a little tight on time. If that deflection happens, it will probably happen closer to 2028 when it's nearer to Earth again. Right now, it's zipping away from Earth. So 4 years is not a lot of time to make sure you can properly do this. But I'm not saying it couldn't work. People are literally working on this right now just in case. Maybe it needs a really big rocket to hit it rather than a smaller impactor. But I don't know. It's just tight, is what I'm saying. It's a very tight bit of time. You could deflect it with a nuclear weapon. We've talked about how complex it would be to do this, but I think in an actual emergency, I can imagine a situation in which space agencies would agree that you would use a nuclear weapon. And you can deflect it. You could basically detonate a nuke next to it, and what that does is it irradiates the surface with X-rays. There's no like blast wave because there's no air in space, so it irradiates the surface with X-rays, and like that surface heats up and gets vaporized, becomes like a jet of vapor, and it pushes the asteroid in another direction.
Right.
Like pound for pound, it's way more like effective as a deflector than like a spacecraft on its own. But obviously there are issues with launching nukes into space. But that could work if we're short on time, which we kind of are. You could opt to vaporize it. Some very, very clever people at the Lawrence Livermore National Laboratory, which mainly deals with nuclear weapons, have done very good simulations on this. And they show that even with a few months to go, you could use a 1 megaton nuclear bomb to essentially vaporize an asteroid of this size. So that could work, that could work. But then you have to be sure you're going to vaporize it, not just break it a bit. And the other option, if it's on the smaller side, if it's like a 40-meter thing, so it wouldn't like outright destroy a city, but it would cause a lot of damage, it may be the best thing to do is evacuate the city once we've nailed down like the exact location. Again, a lot of problems with just doing that. But if you try and deflect it or destroy it and it goes wrong, imagine if you deflect it but not enough and it hits New York City or Moscow, right? You don't want to mess that up. So it might be easier to just evacuate people from the impact site, weirdly. So yeah, you can either deflect it with a DART-like mission, or the time is tight, but you could, or several of them. You could nuke it to deflect it, nuke it to destroy it, or evacuate. That's what we do. I would just like to point out that the odds are still very low. They're probably going to drop to zero. It's probably not going to be a problem. I'm very happy that there's a planetary defense community that are working on this right now, just in case it is a problem.
Me too. And every time I see the headlines about this, I think about that community of very passionate, very dedicated scientists who have been working on this for, a long portion of their careers. And they have been doing very inspiring work. And Robin, thanks for telling their story, for writing about this very important topic. And thanks for coming on the podcast to talk about it.
Oh, thank you so much for having me. Always a pleasure to talk about saving the world from killer space rocks.
Totally.